Greetings fellow gamers. So, as I promised, I'm doing a video about how to make a very basic NES application from start to finish. In this video I'm going to create a Hello World application where you can manipulate the hello text and move it around in the screen. There are many ways how to make an NES application, but I'm going to explore just one of them. I'm sure it's not the easiest, but it's definitely a great way to make NES games that are robust and fast. So grab a snack or something to drink and let's get started, because I think it's gonna take a while. Here I am at my Windows desktop. What? I decided to make this video on Windows. I think what you're going to see here, it will be possible to apply to other operating systems. So okay, let's start. So let's create a folder for our project. So okay, new NES Hello. So for this project we're going to use a very basic NES cartridge configuration, also known as NROM. So that's 16 or 32 kilobytes of PRG ROM, that's the application code, and 8 kilobytes of CHR ROM, that's the graphics. So now let's create our CHR ROM. Well, I want to print Hello World, right? So it's impossible to print text on NES. So in order to write something, I need to create tiles for our letters. So let's do that. And in order to do that, I need to draw them with some kind of drawing program. I think I'm not going to use MS Paint for that, because I haven't used it in a while. But I think I'm going to download and install GIMP. So let's go to the GIMP site and let's download it. GIMP is totally free and it's great for drawing pixel art. So let's download it. Okay, let's download it directly. I hope it's not that big. Oh, it's actually not that small either. Okay, so I successfully downloaded it. So now let's install. Yes. Okay, let's leave it English. Oh, fancy. Okay. The license. Okay, let's skip it. Okay, so I'm going to install it to my programs folder. Next. Oh, there's a lot of options here. Okay, next. Oh, let's create it, why not? Alright, so it's installing. Looks like we're about to finish. So oh, so it's just extracting files, it's not installing anything yet. Alright, okay, it's done. Now we can run the application and start drawing. So basically the CHR ROM is composed of two parts. Two grids of 8 by 8 tiles. So we're going to create those two parts in GIMP. So every part contains a 16 on 16 grid of tiles. So that's like the size of the image should be 16 multiplied by, I need the calculator for that because I'm dummy. Yeah, I can't calculate those numbers in mind. Or maybe program. Oh yes, there's programmers. Bitwise decimal. Okay, this is good. Okay, so now we need to multiply 16 by 8 because each tile is 8 pixels wide. So it's going to be 128 pixels. So each part will be 128 by 128 pixels. Okay, what do we have here? So we're going to leave everything by default. Okay, so we're going to create this image. Alright, where is the... I need navigation. There's no navigation here. So, dockable, where's the navigation? Yeah, alright. So let's fill the screen. So let's fill this with black. Okay, now we need to see our grid. For that we're going to use the configure the grid for the image. Let's pick some bright color for the outlines and let's set 8 by 8 pixels. So we're going to see the grid and let's show the grid. Okay, so here's the single part of CHR-ROM. So for instance, first part will be used for the sprites. As I mentioned, I want to make the word hello move. So I'm going to create this word as a collection of sprites. So now let's draw the tiles. Okay, let's pick a pencil. I need like 1 pixel. Alright, so let's create a... So basically NES graphics are based on 2 bits per pixel bitmap. So basically every pixel is encoded with 2 bits. So everyone say that NES is 8-bit graphics, but in reality it's 2 bits. It's 2-bit graphics. So that means that every pixel has maximum 4 colors. So let's create some tile to put all the colors in. So obviously one color will be black, second would be white. So let's put a white stripe here, and now we need 2 more colors. Okay, so let's make it like dark gray. So that's going to be our outline, and the last color will be like lighter gray. So that's all the colors that NES can use actually. So that's 1, 2, 3, 4. So okay, let's write our letters, because as I said, NES can't draw any text. So we need to draw the text ourselves. So let's draw it. Let's make it white. Okay, so it's gonna be H. Okay, so we're only going to need only 1 L letter, so we don't need 2. And we need O. Obviously I'm not adding all the alphabet, but if you like want to write more text than just Hello World, you probably need to put all the letters. Maybe let's put an outline, so it would not be that boring. Now we're going to need to convert this, because it is an RGB image, we need to convert it to indexed mode. Let's pick indexed. And now we need to, well, it suggests to generate optimum palette, but we need to use a custom palette. And I don't know, what should I pick here? It doesn't matter that much, I guess. Maybe I should pick... Okay, I think I need to pick 16 colors. What would happen if I would pick this palette? Okay, that looks better. Okay, let's export it as a PNG image. So here's our folder. Let's name it sprites BMP. Export it. Let's leave everything by default. Alright. So we have our first part of the CHR RAM. Now let's create a second part. The second part will be dedicated for the... Maybe I will use the same, actually I will use the same file here. So the next part of the CHR will be dedicated for the background tiles. With background tiles is the thing that this first tile will be like entire screen will be covered with this first tile. So maybe I should put something here, something interesting. So let's move our tiles like maybe one row down. So let's draw some, how about some stars? So let's draw some stars. Okay. It doesn't look like stars, but this will do. Okay. Alright. Now we need our letters for the world, because the world will be written on the background, because we're not going to move it. Alright, so let's draw letters for W. Okay, I will reuse the O. Alright, so what left? Alright, so we have our world. So let's add the outline. Okay, that's pretty good, I think. Okay, so let's delete these letters, so I'm not going to need them. Oh, all right. So yeah, so now let's export it as a background BMP. Yep, let's leave it everything default. Alright, so now we have our images. So as you see, they are super tiny. So now we're going to download another application. It's NES Screen Tool. We're going to Google for it. NES Screen Tool. Okay, so let's download it from ROM hacking site. Of course, I will put all the links you will need in the description, so you could download it. So let's download the file now. Okay, let's enter the code. I'm human. Oh, actually I'm not. Alright, where is it? Okay, so I think we could actually put it into our project folder. So let's create a NES ST and unzip the files into it. Alright, so we have our application. So let's launch it. Ooh. Okay, let's run it anyway. I hope it's not a virus, but who knows. Okay, so we have our application. So it's the only application that's exclusive to Windows, because it's basically Windows only, but you can run it using Wine on Linux. So okay, so let's, so as you see, it's completely blank, so it displays the name table. So that's our NES screen, and that's our tiles. So that's two pattern tables. We actually drew those pattern tables with the GIMP. So that's A, we're going to put sprites in A and background tiles in B. So let's import our bitmaps. So let's pick the BMP as tile set. So that's going to be sprites. So let's pick sprites. Hey, it worked. So it imported our sprites, or H. So don't pay attention to this H. It's not going to be visible. So okay, so now let's pick B, and now let's import the second tile set. That's background. Okay, so that's probably what we are going to see on the screen. For some reason it picked the gray color as the main. There's still white here, but it's not the main. Oh, I can actually change it like this. So we imported both bitmaps. So let's create our CHR ROM, and we're going to do that by picking the pattern and save CHR. So we're going to save both tables, so that will be 8 kilobytes. So let's, I don't know, tiles CHR. Let's save it. So we have our CHR ROM. So we have our graphics. So now let's move to the next step. That's going to be writing some code. But in order to build a PRG ROM, we're going to need some kind of a assembler application that will assemble our graphics and code into NES ROM that we could run on an emulator, or maybe play the so-called game on the NES. Okay, so we need the assembler. So for that there are a lot of options, but I think, well, in my personal opinion, the best assembler is the C865, because it supports not only the assembly language, but also you can code with C on the NES with it. Also it supports TAR 2600 and other computers that uses the 6502 CPU. So let's download the assembler. So let's CA65. So it's basically it's not only assembler, it's a collection of tools. So let's see if it's easy to install, because on Linux, for instance, it's pretty easy to do that, because you just write sudo apt-get install C65 and it's done. But I'm not sure. Alright. Okay. Yeah, so let's download it. Ooh, SourceForge. I haven't seen that in a while. Why it's okay, so let's drag the window here. Alright. So that's supposed to be the so that's all our binaries. C865, that's what we're going to use, and there's a linker. Alright, so that's looks good. I think that's gonna work great. So let's create new folder. Let's call it C865, and let's extract the files here. Where are the files? There they are. So let's extract them. And it's copying. In order to use this compiler or assembler properly, we need to add a path. Okay, so we need to edit the system environment variables. So environment variables. That's the one. So we need to go to the path. So that's my user and that's the global stuff. So we need to add a new path. So it would be the programs CA65, and what was the folder that it's bin. So it's, come on, so it's the programs CA65 bin. So in your system it might be different folder, but that's what is on my system. So okay, and okay, and okay. So let's test it out. So I'm going to open up CMD command prompt, and let's go to the to our desktop NES. So this is our folder. So let's call CA65, and it says no input file. So the assembler is working. So now we need to start. We can actually start writing some code, but we need an editor for that. And I don't know, I could actually download the Microsoft's Visual Studio Code for that. But with this video, I want to show that you can actually use any text editor to write your code. You don't need to have some kind of magic integrated development environment to be able to make applications or games or whatever. So I'm going to use a very basic text editor. I could actually use the Notepad, but the Notepad has two disadvantages. It doesn't show the line numbers, and it can't color keywords in your code. So I think maybe I should get the, well, I could actually use Vim, but I guess it's a bit complicated and maybe it's not great for new users. So I think I will get the Notepad++. So it's like Notepad, but it's a bit better. So I don't have it on my system, so let's download it. So, okay, there's a lot of different versions, so let's grab the latest one. Alright. Download it. Okay, it's going to install. Let's install it in English, of course. Yeah. Okay, let's install it into my D drive. So, okay. There's a lot of stuff. Let's install everything. Let's create a shortcut. Okay. That will do. Let's run it. Alright, we can start writing our code. Okay. So now to start writing a basic NES application, we need to create a memory configuration. So we need to write a memory CFG file. So basically we need to write like this: memory. This file will show the assembler how the memory on NES and the cartridge is like structured. So let's create another thing, segment. So we're going to use these segments in our code. So let's start from the memory. So first block will be header. So this header is actually it's only used by the emulators. So it's not going to be important for if you want to run your application or game or whatever on the real hardware. It's only going to be important for the emulator. So let's specify where it starts, and it starts at the very beginning of our ROM. So this $sign means the number will be in hexadecimal mode, so it will be 0. Okay, so the size will be also $0010. Well, it's actually not 10. We're now in hexadecimal mode here, and like 10 is 16 actually. So let's fill yes, and type is read only. Okay, now we have header. Now let's specify the PRG ROM. PRG ROM. So for this project I'm going to use a basic, probably it will be enough to have a 16 kilobyte PRG ROM, because we're not going to create a Super Mario World here, so 16 kilobytes will be more than enough. So let's specify start. Let's specify where the our PRG ROM starts, and it starts actually not at the beginning of the. Actually, I need to run calculator. Yeah. So it actually doesn't start at the beginning. The beginning of the PRG ROM is, it should be in hexadecimal mode, like this address, 8000, but it's in hex. It's actually like 32 in, yeah. So we need to start from the middle of the PRG ROM with 16 kilobytes. So let's add the 4000. So this is 16 kilobytes in hexadecimal mode. So yeah, so we have C0, yeah, so this is the beginning of our 16 kilobyte PRG ROM. So this C00. Alright, so now let's specify the size of the PRG ROM, and it's actually not 16 kilobyte, it's actually a bit less than 16. It's like, for instance, if I write that 16,000, like 16,384, so I need to subtract 6 bytes and I will get this number. So that's going to be our PRG ROM size, 3FFA. Alright, so now let's put everything like before. It's also type read only. So why I subtracted those 6 bytes? That's because I'm going to use those 6 bytes for the vectors section. So vectors are going to store the addresses of the important code points that the NES needs to know, like where your actual application starts. The vectors are start at the end of the PRG ROM, so that was like if we add if we add our size 3FFA, we will get the beginning of the vector, so it's FFA, and the size is 6 bytes. So it is 3 addresses. Each address is 2 bytes, so in total there are 6 bytes. So let's fill them. Fill, yes. Okay. Okay, so now we need to specify the CHR ROM, where the graphics are. Okay, so CHR ROM is like very normal. It starts from 000, and the size is 8 kilobytes, and in hexadecimal mode it will be 2000. So yeah, that's why hexadecimal mode is nice, because like the sizes are like nice numbers. Like like for instance, if I write the 2000 in hexadecimal mode, like looks pretty, but in decimal it's like 8198, so it's not that pretty. So the hexadecimal mode is like nicer to use for the sizes computing. So let's fill it. Fill, yes, and type is read only. Alright. Okay, now we need to start specifying our RAM, and we're going to begin with 0 page. So 0 page is the first page in our RAM, since the RAM is, let's say the RAM is divided into sections of 256 bytes, so that's the first section. So that's the beginning of our RAM. So the size is 100, but it's also in the hexadecimal mode, and it will, and if I would write 100, we'll see it will be 256. So yeah. Type is read and write, rewritable. So we can actually read from it and write it. Let's specify CPU stack. So CPU stack will be after 0 page. So it starts at the right exactly after the 0 page. So it's gonna be 100. The size of it also will be 256 bytes. So the stack basically is the storage. So basically, after you execute a subroutine, the CPU stores a return address into the stack. So for example, if you have a subroutine, you execute it and it stores the point where your code was before you execute the subroutine. So when the subroutine ends, the CPU can return back to that point. So we need memory for that. So we're going to use this section of 256 bytes for the stack. It also will go, but it will going to work automatically. We don't need to worry about it. So, all right. Now it's time for OM. So that's the storage for the sprites. Let's start at the 200 because we already have two blocks. So okay, so the size of OM is actually it's actually less than 100. So it's going to be FF, and that is 255 bytes. Yeah. So that's also going to be rewritable. And last but not least, the RAM. So that's the also, well, I need to mention that 0 page is also the RAM, but it's used for the stuff that's that is used the most, and the rest goes to the RAM. So let's start at the 3rd page. The size will be 500. That is 500. It's interesting. 128. If I add, we have 3 pages. So if I add 300, we have exactly 2 kilobytes of RAM. So that's that. Okay, I made a mistake here. So that's exactly what is left. So okay, so let's write the define. Yes. All right. So now let's specify our segments. The segments will be used in the assembly code. So let's write header. So we're going to use the memory header. Load. We're going to use it. Let's specify again type read only. And let's specify the segment for our code, actual assembly code. Let's load the PRG-ROM and type read-only. Okay, so now another segment will be for the read-only data. That's for the constants and stuff. It's also in the PRG-ROM. Alright. Also type is read-only. And it's for some reason is optional. Okay, let's specify the vector segment. Load vectors. Type rw and char or chr will be named as chars here. So load chr rom, type read only. Let's specify 0 page segment. Load zp, type zp, optional yes. Okay, now two last segments, so it's om for the sprites. Load om, type bss, optional yes, and the last will be bss. Load ram, type bss, oh. Optional yes. That's it. So as you see, I've finished the configuration file, so let's save it. Okay, so where is the NES Hello folder? So let's name it CFG. Maybe we need the quotation marks. So now we are ready to write actual assembly code. Let's go to the, where's the folder? NES Hello. So we have the configuration, we have our tiles. So let's create a new text document and let's name it, I don't know, maybe game. I don't know about the extension. I could use ASM, but I think it's proper way for the CA65 to use S as the extension. So let's name it to S and let's drag it to our editor. I don't know if it's going to understand that now writing assembly code. Let's try to specify our segments here. Segment. No, it doesn't look like it understands. Well, I guess it kind of does. That's kind of hard to say. So let's specify our segment. So let's start from the CHR ROM. So we have a segment chars. And here, for this segment, we're going to include our, like, this tiles CHR file. So for that, we're going to call inc binary, inc bin, and here we're going to write tile CHR. Tiles. So that's our file. We're going to include this this CHR ROM into our main NES ROM. So now, next important thing is header. Segment header. We already specified it here, you see. So this segment is very important for the emulators. So the emulator would know what kind of mapper we are using. Well, we actually don't use any mappers here, so we need to point that out. So it's gonna be some bytes. So in total it's like, I think it's 16 bytes. So this instruction byte will tell assembler that's going to be a byte sequence here. So it's going to be 3 bytes for the NES letters, NES, and this hexadecimal number. All right. Now another byte. Okay, this will specify this, like this hexadecimal one will specify that this is a 16 kilobytes ROM. For the 32 kilobytes, we would need to put 2 here, but since we're using 16, this will be 1. So let's add another byte, and it will be the size of CHR ROM. So CHR ROM, since it's 8 bytes, it's also going to be 1. So we already have 1, 2, 3, 4, 5, 6. So we still need 10 bytes. So another byte will be some kind of a collection of bits. So this percent sign means that number will going to be binary. So basically it's ones and zeros. In this case, I'm going to put 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 bits of zeros. All right. And I think this is NES version 2 header, and it all going to contain 0, 0, 0, 6 zeros. I mean, I could just write without the $sign, but I will put it there anyway. So okay, so that's 6. So this basically tells what kind of a mapper is used and like other specifications. So the last bit specifies what mirroring is used. So now currently, if it's 0, horizontal mirroring is used. So okay, so let's specify next segment. So let's specify vectors. So as I mentioned, the vectors is holding 3 addresses. It will hold the 3 positions in this let's say in this file where the 3 types of code could be located. The first, so it will start with word, since these addresses are 16-bit. So if 8-bit number is byte, then 16-bit number is word. So it will contain 3 words. So the first one is NMI. NMI stands for non-maskable interrupt. So this thing starts after NES draws a frame. NMI is called between the frames. Okay, I will talk about it a bit later in detail. So first one is NMI. The second one is reset. The reset is called after basically you turn on the NES or hit the reset button. So after you turn on the console, the NES looks at this 16-bit number in this vector segment, and it knows, I need to go to the reset and start executing code from here. So the third one is I think it's for IRQ. So it's basically some kind of code that the additional hardware in your cartridge basically wants to execute. So it's not important. So we're going to put 0 here. So we are going to only use the NMI and reset. So okay, let's specify segment. That's called code, and it will start with the reset. So basically this vectors reset will point to this 18th line. Let's write some boilerplate code. That's the initialization of the system. So basically this is turning off the decimal numbers. So let's load. So this instruction, assembly instruction, LD means load, and it loads into the CPU registers X something. So let's load the sign means it's a value. So let's load a value to the register X, and this value will be a hexadecimal number since I'm using the $sign. FF, so that means it's a 255. Actually I could write like this, 255, doesn't matter, right? So now I will transfer X register to the stack. So I will store this contents of this X register to the stack pointer. So let's store it. Now we're going to increment the X register. So if you increment an 8-bit register 200, which has a 255, you will get 0. So now the contents of the X is 0. We could actually watch that in the debugger a bit later. So okay, so you know what? I actually want to try this out. Let's specify NMI, the non-maskable interrupt, and we will try to compile. Maybe it will actually work. We will continue writing this later. Now let's specify NMI. So as I said, NMI is called after the NES has finished rendering one screen on the TV, like one game screen. Like it finishes and it calls the NMI. So inside of this interrupt there should be code like to prepare another screen. So basically NMI is limited. It has a limited time to execute some code. Even though it's limited, some developers actually put the whole game logic inside of it. So for instance, Super Mario Brothers are completely located in NMI. So all the game logics and drawing of the sprites are there. So we need to create a loop here. So what it does, it will create some kind of infinite loop, this reset. So let's call it forever. So this forever is a label. So it labels the 25th line of code. So basically reset is also a label. Let's execute a instruction jump, and we will jump to forever. So what does it mean? So basically, when you encounter this, it will jump to this and it will execute. So it will go forever. So basically reset starts something like it basically initializes your system and creates a forever loop. And from time to time, the NMI will be executed. So some of the games, let's take Super Mario for example, it will initialize the system, some kind of variables, and it will leave this loop empty and do everything else in the NMI. So basically we are going to do the same because our example is pretty simple. I just want to compile the application, so let's put RTI. This means return from interrupt. So NMI is interrupt and this is return from it. So it's like a subroutine. So this means it's a comment. So this line doesn't do anything. It's basically for humans that will go to read the code. So let's make it distinction that's separate thing. Alright, now we actually can try to compile this thing. Okay, let's save it. Now what we're going to do is to create a batch file. So this file will going to run the compiler, run the assembler, and it will create an NES ROM. So let's call it compile. Of course I could use a make file, but I don't want to install make or other building system. I'm just going to use the Windows batch files to keep it simple. So compile that. So of course it's not a great way to do this, but it will do. So let's drag it. Let's make this window a bit bigger. Let's drag the compile bat to our. So okay, I will try to create a batch file. So basically we already specify the path for our compiler. So basically if I run CA65, it should still work. So it works. So let's put CA65. Let's put the game as the file that we wrote recently. Let's put, I don't remember what does it mean. So basically it will going to output the, I think it's for debug information, is G. So basically as O says to the assembler to create an object file. Game O. Alright. Actually, let's save it and let's try to run it. Let's see if it actually creates something. Right? And it created in a file of 16 kilobytes. So we actually can execute it from here, compile. That means everything is alright. So if I here write something, some nonsense, blah 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 blah. Okay. And if I will run compile, it says that on the line 16 there is no yeah, it lacks that sign. So basically it's some kind of garbage. Yeah. So we need to delete it, and if we will run compile again, it's all good. So our compiler is working. So let's continue. Now we have object file, so we can't do anything with it. Now we need to run linker. So it will be LD65. Okay, it's probably, so its outputs, oh, it's for output, so it will create a NES ROM. We will use our configuration that we created previously. So it's gonna be memory CFG, and we will specify the game O, the object file that we created. And that's it. So if we will compile that, bam, okay, says segment chars does not exist. ROM missing memory there, char. Memory area assignment for segment char. Think I made a mistake here. Let's see. Oh, I think it's not char, but it's chars. So let's fix it. So let's compile it again, and it's all good. So let's see, what do we have here? Okay, we have the NES file. Now we need to try it out. So for that we need to get an emulator. And I think the best choice is Meson, because it has a great debugger. And so let's download Meson emulator. Let's pick the Windows. Oh, it's dev build, okay. That doesn't matter. Oh, apparently I tried to download it previously. So let's open it up. Okay, let's put it into the project folder. I hope it's not some kind of installer. Oh, okay. Run it anyway. Oh, so I already tried this to run my game. So okay. Let's try the ROM. And as you see, nothing happens. Let's try to debug it. Okay, so let's pick debugger. Ooh, there's a lot of options. I see some kind of a jump here, but nothing else. So what's going on here? So it seems it's only jump. So those initialization lines were not included here for some reason. Maybe, no. Okay, so the debugger doesn't show anything. So let's try to change the batch file. Let's try to add some additional parameters for the linker. We need to export. Let's try to export debug file. Game like this. Maybe also let's try to export labels if the Meson, I'm not sure if Meson will understand the game. So game labels. Let's put the txt. I think that should do. Okay, so let's compile it again. And let's open up the ROM with Meson. And maybe this time the debugger will show more information. Yeah, there it is. So now we can see the labels and the line. So let's try to debug it for a second to see what is happening here. So let's put a breakpoint. So toggle breakpoint. So basically that means the debugger will stop the execution of the code at this line. So if I restart the game, reset, and we are at the line, and it actually shows what this line does. So you can actually learn some assembly by debugging the code. So let's set interrupt disable. So okay, so we can click F10 or just click this button. So we're gonna step one line. So now we're at the clear decimal mode. Well, decimal mode doesn't work. So okay, so this line, as I mentioned before, it should load 255 into CPU's register X. So we see the register here. So what will happen if we execute this line? So we see that FF appeared here. So we loaded the value into this CPU's register. All right. So now we need to transfer this value to the stack pointer. I'm not oh, okay, here it is. So stack pointer. So apparently I think it will change. So let's execute it, and we should see FF here as well. Will it happen? Yes, it did happen. So as you see, now it should increment this value by 1, since it's a maximum value for the 8 bits. So it should reset to 0. So let's step it, and boom, we have 0. So our code actually works. So now we are in the eternal loop. So as you see, we are at the jump. So if I execute this line, it will jump here, or probably it will stay in place. So let's do that. And yeah, it stays in place because label doesn't count as actual code line. It's just, so yeah. So let's add some more code. So let's close the emulator, and let's do some more coding. So basically we need to finish initializing the system. So we need to warm up the PPU, and for that we need to, for starters, we need to store the 0 STX, the contents of X register, which is 0 now. We need to store it in several addresses. So one address, so as you see now I store, basically you can store at certain memory address. So $, as I mentioned, is it means that it's a hexadecimal number, and now I will specify a address which stands for the this address controls the basically NMI. So basically I will disable the NMI by writing 0 to this address. if you store a byte to this address, you can change some settings for the NES. Maybe I will address that later. So, okay, so we stored 0 into address 2000. So let's store into, so by storing a byte into this address 2001 stands for PPU settings. So now we are disable rendering, so the NES won't draw anything. All right. So now we need to disable IRQs. I don't think we're going to use them anyway. So now they are disabled. Now we need to warm up the PPU. So PPU is like this graphical processor that draws everything, draws the sprites. So we need to wait about 2 frames. There's a certain time that we need to wait before the PPU is ready to draw anything. And to do that, we need to create a similar thing like this forever loop, but we're going to like this: v blank wait 1. So we're creating a label here, and we're going to check a 7th bit. So this instruction bit checks the very highest bit of the byte that is stored in this address. And this address is the PPU status, I think. Yeah, that's the PPU status. So basically we need to check the highest address of the PPU status. So that means the PPU is finished drawing 1 frame, and it will set that bit to 1, and this will work. And if the bit is not, if it's not set, then we're gonna jump with this instruction to back to this label. So v blank. So basically this code, what it does, it waits until a frame is transmitted to the CRT TV. After that, we can actually start clearing the memory. So we need to clear the RAM of the NES. For instance, if we want to clear it, then for instance, if we create a variable in the memory, it will have some kind of weird value. So in order to prevent that from happening, we need to clear the memory. Let's load a 0 value to the register A. Yeah. And now let's store that value. This means store value that's in register A into address 0. So basically that's the 0 page, and we're going to use the index. So I wrote X here. That means it's going to use the value that's in register X. So we're gonna, yeah, I think we need the label clear memory. All right. So basically we're going to increment this X. So let's write X. So it's gonna increment X. And now we're going to check. So basically we're going to increment the X register until that point it turns again back to 0. clear memory. So that means if the X is positive, we need to jump back to this label. So okay, let's try to save it. Let's run it and let's see how it works. Let's compile it. Alright, it compiled without any errors. And let's run the emulator. And it doesn't do anything yet. So okay, I have my breakpoint, so I can actually reset. So let's go to the, so okay, it doesn't show anything. So as you see, it shows what values there are, so what settings you can change. So basically, as you see, it's this 2000s PPU control. So yeah, so you can see all the settings you can change by changing the bits. So now all the bits are set to 0. All right. Okay, so let's add the breakpoint here. So we're gonna jump right to this point because it's like it's going to iterate for several cycles. So let's continue. Boom. So now I'm here. So okay, so A register is 0. So we still, all right. So now let's see what can we check what's in the memory actually. View memory viewer. Okay, so we're not gonna see anything. Well, I think I can actually, probably I can change it. Maybe I can. Yeah, I can. So I can actually set something in the, so I'm actually now currently editing the memory and sending random stuff in it. So let's see if our code will clear that stuff. So let's put it here and let's step through the code. So now I think it should clear this 20, and it did. So now the X is incremented. Now we're gonna jump. So it checks that X is 1. So if it's positive, then jump to this line. And yep. So now we're gonna store the 0 here. Yeah. So let's go through the. Huh, interesting. Why why didn't, so it's a bug or what? So basically it will go, actually I can put another breakpoint here, and let's see how many bytes in memory it will clear. So let's remove this breakpoint. And yeah, so as you see, it cleared all the, well, except this 20. It cleared all the bytes in this section memory and up until address 100. So we need to deal with that. So basically it cleared only a small section of the NES RAM. So okay, let's close the debugger. And let's get back to the code. We need to add another section of memory. So basically another 256 bytes in the RAM. So basically it's not sections, it's actually page 2. So now we clear the 0 page. And now we're clearing the page where I think the stack is. We're going to skip the page 3, which is where the OM is, basically the data for all the sprites. Or you know what? Let's add it here and fill it with zeros, and you will see what's gonna happen. It's gonna be interesting. Okay, so let's add all the pages. Basically, we have like I think we have 7 pages. No, we have 8 pages. Basically, where's the calculator? So basically, if we let's go to hex, or maybe we can. So basically, we have 256. Let's multiply it by 8 pages, and we have, boom, 2 kilobytes of RAM. So this way we're clearing the those 2 kilobytes of RAM we got in the NES. So page 4
and page 5 and page 6 and page 7 and the last page. Alright.
We cleared the memory. Now we need to wait for another frame. Let's copy this thing and put it here. So I'm gonna change the label because we can't have identical labels. We need to give it the name vblank wait2. So yeah, that's also. So let's save it. Let's try to compile it. Compile, everything's all right. So let's try to run it, and let's see what happens. So nothing happens yet. So let's try to reset the game, and let's see how it will clear the memory. Alright, view in memory viewer. So okay, so let's jump to the let's jump here. Let's add a breakpoint. We'll remove the breakpoint from here, and let's continue. Boom, as you see, it cleared all the bytes up until here. So I don't know what. Oh, so it's basically already the PPU control address. So basically it cleared all the RAM. So yeah, the RAM is cleared. We waited for another frame. So now we can actually stop. We can actually do something that's gonna be visible. So let's turn that thing off. All right. So now we can try to enable. Okay, let's enable the NMI interrupt because when I stored the 0 into this address, I have disabled the NMI, so I need to enable it again. So before this forever eternal loop starts, I need to enable the NMI. So to do that, we need to load this. We're going to load a value that is binary. That means it's ones and zeros. So I need to load this value 1 1 1 1 1 to the address 2000. Let's actually see what's gonna happen. So let's compile it, and let's run the Meson emulator, and nothing happens. Let's see the debugger, what's going on here. Alright, game reset. So it actually created from my binary line created a hexadecimal value. So let's look at the code, and it will be clear what those bits that I set to 1, what they mean. The first bit means, so it means the NMI is on, and the fourth bit means that the background graphics are in the, so basically this bit means the order where the background graphics is. So let's open the Screen Tool. So basically it sets that the background tiles are in this B and not in A. If we leave this as 0, the background will be here at A, and now it's gonna be B. So the way I created the CHR run. So basically, let's put something to the NMI, so it will do something for us. Basically, this code that I'm going to put now, we're going to prepare for the next frame. Well, we're not drawing anything yet, but let's load let's load the same value that I loaded here at the end of the initialization. So let's load the 4 zeros. Yep. So basically load that to the address 2000. So we're keeping this setting. Alright, now previously I set the address 2000 to 0. So let's load this value 0001110. Something's missing. I need four ones. Alright, and store this value into address. So that's the PPU settings. We stored something to the PPU. So I think that will do something for us. Save. Alright, listen. So as you see, the emulator had had some kind of a green screen. So let's try to compile. Everything checks out. No, it's still. Ooh, what do you know? It actually worked. So as you see, we see all our sprite here. So because I set the zeros to the OM page, basically I set all zeros. So basically NES has 64 sprites, and the coordinates for all of the sprites now are 0. So we see all the 64 sprites here at the corner of this screen. And because the background tile 0 is like stars, now it covers all the screen. So yeah, pretty cool, huh? So now let's try to change how the OM page of the memory is filled. Let's set some other value than 0, and let's see what happens. Alright, so let's turn that off. So basically that's enough for for a Hello World. If we could actually stop here, but I will continue. The page for the, so this page is 0 page, this is stack, and this is OM. So now we need to grab this line and, like, I don't know, put it here. And now we're gonna load some different value to the register A, and that will be, let's add a FE. So FE is a, a value for 254. So it will set both X and Y value is to 254, and that should be outside of the screen. So now we won't see it, the sprites. This value will hide them all. Let's save it. Let's compile and let's run lesson. Oh, what happened? Alright, that's interesting. Let's check the debugger. Alright, let's go to the toggle this line. No. Okay, this is good. It's memory. And let's see what happens. Yeah, it filled the page with FEs, but nothing happened. Maybe it is because actually during the NMI we actually need to activate the transfer of data from the OM section of memory to the CPU, so it would update the sprites. Every time the frame is finished during the NMI, the OM is transferred to the CPU. So let's activate that. Let's set basically the address of the OM. So basically that's the value of the, I don't know what should be the order, maybe. Okay, let's try that. Let's store the address. The address of the OM is a 16-bit number, but since the CPU registers are 8-bit, I can only store the lower and higher bytes. So that's the lower byte. So let's store it to the address 2003, and I want to put a upper part of the address into here. So I'm gonna load O2. So if we combine these two parts, it will be this address. So I'm gonna store the upper part of the address into address 4013. So yeah, let's see what's gonna happen. Okay, I saved it. Now let's compile it. Everything's good now. Okay, so let's run it again, and the H is gone. So all the sprites now are gone. Well, basically they are somewhere here, but what this did, it basically with after every frame the sprite data is updated. So we can actually go to the debugger and we can actually see what's this address is. So it's sprite direct memory access sprite DMA. Basically it activates the sprite DMA and it copies basically links the data in memory in the RAM to the CPU. So yeah, so now we can actually change the data in RAM. Basically we can change the data in this section of RAM that's called OM and form our hello, basically a single word from sprites. So let's actually do that. I didn't load any palettes, so apparently there are some default values. I guess it still draws something as you see, it grabbed some default values, but I will load palettes later. Now let's form the hello world. I could actually create a subroutine for that. How should I call it? So let's call it, okay, let's add the command that maybe we could write here, subroutines. So basically that's command for humans, doesn't do anything in code. Let's call it update hello. Alright, so we created a label, and now I'm gonna add a command return from subroutine, return subroutine. So it's similar like this RTI, but this one returns from this interrupt, and this is returning from this subroutine, but we're not calling it yet. Well, actually we could call it. So since this example is simple, we can put all the code in the NMI, so it will execute it after PPU finish drawing a frame. So let's call a subroutine. So for that we can execute the command jump subroutine JSR, and we just gonna type the name of it, update hello. So basically this will gonna jump here, and this will return back here. So we can actually have separate blocks of code that do something. So those blocks are called subroutines. Let's try to form the single sprite. Well, basically let's put an H somewhere. So basically how sprites are organized, they are like 4 bytes of data. So first byte is the Y coordinate. Let's create a variable. For that we need to specify segment. Actually it would be nice to put the variables into the 0 page, but I don't want to do that. Let's do that before code. So let's create let's specify segment, and that should be BSS, so it's a regular RAM, so it's not the 0 page, it's page 3. Now we're gonna specify a variable. Variable is basically a label. Basically, yeah, it's a label. So let's call it hello. Maybe it should be like lowercase. Hello Y. So we created a label in a RAM that's gonna point to a resource that's a 1 byte. So basically it's gonna this hello Y pointing to a 1 byte. So basically we have a 1 byte variable. So we can change that 1 byte in RAM. So let's create another one. Hello X, and also 1 byte. So we have 2 bytes. So we have 2 labels that are pointing into 2 bytes in RAM. So let's actually put something into them, and let's do that like after the. So basically we have our initialization, and let's put it here. So let's load a value. Let's say 100, and store it into the hello Y, and let's store same value that's an A register into hello X. All right, so now we could try to use those variables to specify data for the sprite. let's load the value from the RAM that we stored in the initialization into back to the register A in the subroutine. So let's load hello Y, and now let's store it into address, into the memory address 200. So that's the first byte of the OM page. So let's store it here. Now let's load, I don't know, 0. So basically the sprite is 4 bytes. So second byte, the first byte is Y coordinate. The second byte is the frame. It's the tile. So first tile was, I think it was like OpenCHR tiles. So let's, yeah, so first was H. So let's store that into 201. All right. And now the third byte is a attributes for the sprite. So basically the information if the sprite is flipped, what kind of palette the sprite is using, but we basically could store 0 here. So we can actually, we don't need to load anything because it's already 0. So let's basically store that into 202. So that's third byte. And now let's load the hello X, so the last byte, the fourth byte, will be the X coordinate of the sprite. So let's store that byte into the 203. So that's 0, 1, 2, 3. So we have 4 bytes. All right. So let's try to compile it. And let's close it. Where's the NES Hello? Let's run the messing. And well, that's interesting. Doesn't look like it's like 100. Basically at the top of the screen for some reason. So basically Y coordinate is not working like it should. So let's see what the debugger says. Okay. So let's, oh, you see, it points that hello Y is 0 and hello X is some kind of a value. But why is it? Load. That's interesting. Okay, let's put the breakpoint. Well, actually we have the breakpoint here. So let's game reset. Let's see what's going on here. All right. So we have 64. That's 100 in decimal. All right. Oh. Okay. Let's jump it. All right. Now the memory is empty. Let's see the memory. What's okay? So we have like third page. No, it's fourth page. I think. So let's step it. Boom. Now it should store it here. All right, 64. And now it should store it here. All right, everything checks out. So where did I made a mistake? That's interesting. Okay, everything's good. So yeah, jump forever. So now I need to, so since it's gonna go forever, I need to go to the subroutine and put the breakpoint here. So let's go here, and yeah, so it's still 64. So let's store the, so that we can actually see the OM. That's the OM. That's probably the stack. So let's step it. So now it should store it somewhere here. Okay, 64. Now load the 0. Alright, okay. Okay. Okay, 0. And now it should store it here, 64. So what is going on? Okay, let's remove the breakpoint. Well, now it seems it's alright. Okay, what will happen if I remove the breakpoint? Oh, that's weird. Now it's alright. Yeah, that's what I call magic. Okay, so basically our H is at the place where I want it to be. So let's add all other letters. Okay, let's go back to the code. Alright, so we have letter H. So, well, in programming it's bad practice to copy and paste, but since it's just a simple example, let's copy and paste the blocks of code. So basically now we need to increment x. So yeah, so basically what should be different about it? We should change the address. So now it should be 4, 5, 6, and 7. And here should be 1. And we should we should increment this x by 8. But we should not change the variable itself. We should basically change what's inside of this CPU register. So for that, we need to clear the carry flag. So it's a special flag that's that could be filled if you, for instance, add a very big number. So we need to clear it. Or else, if you, for instance, if you add something to a value in the register, it might, like the carry flag might ruin that value. So let's call the command adc. Yeah, let's add 8 to the value that's inside register A. And it's gonna store that value into the address 207. So let's save it. Let's compile it. Boom, it works. Let's close. Now let's see what happens. Oh, but why it's so dim? That's interesting. Okay, we will solve the problem later. So we have 2 letters. So let's add some more. So let's copy that again. Okay, it's never do that. Never do that. But for learning purposes, it's okay to copy code. Alright, so it's gonna be 8, 9, 10, and 11. Ooh, it's not gonna be 8, 9, 10 because we're using the hexadecimal mode, so it's 9. So it's it's A, because hexadecimal numbers contain 16 digits, so the digit that goes after 9 is A, and instead of 11 it should be B. Yeah, that's okay. So now we're gonna put letter L, and the index for letter L is 2. And here we're gonna add 16 because like H was at the 0, then we added 8, and we need to add 8 again. So now it's gonna be 16. Notice it's in decimal mode, so it's normal 16. It's not F. All right. So let's compile that, and I wonder if, can I reload? Oh, I can. Oh, okay, interesting. It's like every letter has a different palette for some reason. I don't know why. Okay, so we have hell. Okay, let's add more letters. So let's copy that again. Alright, so now we need to increase that number. We need to add 8 again, so it should be 24. So it's 16 plus 8, 24. And we need to increase those numbers, so it should be A, B, C, D, A, B, C, D, E, and F. And basically it's the same frame for both L's. So yeah, so let's save it, compile it, and let's reload the ROM. Game reload ROM. Hell. So yeah, every hello has hell inside. So okay, let's add the last letter. So we're not gonna leave hell. So let's, okay, so after F it's gonna be 10, 11, 12, and 13. Okay, so we need to add 8 again, so it's gonna be 32, because like 5 letters and 5 times 8 is 32. So, and the index should be 3, because like 0, 1, 2, 3, so should be O. And yeah, that's it. So let's save it, compile it, and reload the ROM. So yeah, we have colorful hello. For some reason, I don't know why it's colorful. It shouldn't be, but it is. Yeah, so maybe I should specify the palette, I think, because I don't like how this looks like. It's so random. We need some. Maybe I'm missing something. Why I have the feeling that I'm missing something. Okay, let's load the palette. Maybe I should create a subroutine. That would be nice. So let's create another subroutine. I like to separate subroutines with this type of comment. It's not necessary, but I like it that way. So let's create a subroutine. Load palette. Load palette. So that's label. Let's add return from subroutine. So that's very important. Now we need to enable writing to the PPU by reading. Let's read. So basically we're going to load the contents from address 2002, and by doing that we're going to activate writing to the PPU. So now we need to specify the address where the palettes are, where we are going to write some data. So now we need to specify the higher byte. Oh, sorry. So it should be 3F, and store it to the address 2006. That's the where the basically it stores the addresses. So if we can specify the lower byte of the address, and if we store it into the same address, it will combine those two values together, and we will have 3F00. Okay, so we have address where we want to write our palette. We need the data for the palettes. So palette is it's a collection of colors like this. So we have total amount of colors, and the palettes are 4 palettes like that for the sprites, and another 4 palettes for the background. So basically 16 plus 16, so 32 bytes. So we need to specify 32 bytes for the palette. So we can actually put those bytes into the ROM. We actually have a segment that I haven't specified. Let's put it after here. It doesn't matter probably. I haven't tried it, but I think it doesn't matter. So let's specify the segment. It's called row data. Well, it was in the memory config row data. So in this segment, we're going to put the data that's not going to change. It's not variables, it's basically some constants. So basically we can put values for the hello sprites. In this case, we're going to put our palette data. So let's name it. So let's create a label palette, right? And let's specify bytes. Byte. So now I need to specify 16 bytes. I don't need different colors. Let's make the background, I guess, black. So for black we have 0F. So let's put it here. Now, okay, so what color should I use next? So for the outline, let's make it, let's make it fancy. Make it red. So it's gonna be 16. And okay, for the main color, let's make it white. So it's gonna be 20. And for the okay, so I don't use the other color, so I don't know, so let's make it purple or something. 13. Okay, so we have single palette. So let's copy that, and we need to copy 1, 2, 3. So basically I have 3 palettes and 4th. So I can actually repeat that. Alright, so there you go, I have the data. So basically I think those are for the sprites and those are for the background. So basically all the palettes now are identical. We need to load them into the PPU. So I need to iterate through that palette data and store it to the address 2007. I can actually write here store 2007. Now I need to use a X register as a index. So let's load into X 0. Now, like I did with the clearing of the memory, I can do the same thing here. So I will increase X. So it's gonna increase, and after it's increased, so let's put this here. So I'm gonna increase the X. So now I use this instruction cpx. That means compare X, and I'm gonna compare X with 32 because we have 32 bytes of palette data, and I'm gonna compare X with 32. I'm gonna check if it's 32 or not. So if it's not 32, it's like branch not equal. That means branch not equal. It's not 32. So I'm gonna jump. I'm gonna create a label here. Let's create a special label that it's limited to this subroutine. Let's create label loop, and I'm gonna if it's not 32, then I'm gonna jump here. So it stores something, increments the value, and compares if it's 32. If it's not, then it goes here. If it's 32, then it's just basically finishes. So let's write loop. All right. Now we need to get a value from the palette. So we're gonna load to the register A palette. So that's what we specified here in the ROM. So let's load palette, but we're going to use the index, and it's going to be a value from the register X. So load palette X. So it's gonna be so it's when X is 0, it's gonna be this value, like 1, 2, and so on until it's the end. Don't pay attention to this byte because like you need to write this byte with every new line. If I'll just put this, like cut this and put it here, like I would not need to write this byte just for the code to be clean. So yeah, so it should supposed to load this palette and store it to 2007 address, and by storing the PPU automatically increments its address, and basically you can actually store it to the same address and it will automatically increments, so you don't need to worry about where actually it stores this value. So now I need to call this subroutine at the initialization somewhere, like I don't know, maybe here. So jump subroutine and load palette. Boom. So it should execute this subroutine, then set the values for the hello X and Y, and I think I'm actually missing something. So that should be, yeah, after the I need to enable sprites, so I need to copy this thing from here and put it here. So yeah, so I forgot to do that. Okay, so after the NMI is executed, I also need to clear the this address that we used, like this 206. We need to clear it at the end of the NMI. If I'm not gonna do that, the screen might display some kind of garbage. So I need to load 0 and store it to the 2006 2 times, so it will clear upper and lower bytes. That's it. So let's try to compile it. And let's try to reload it, and let's see what's gonna happen now. I think it's gonna be fun. Let's reload. Yay! So now everything's like using the same palette. Maybe we could try to set a different color for the sprites. I mean, it's like clashing with this. Maybe we should change the background, I think. Maybe let's make the stars like blue or something. Okay, I think the second is the background. So let's try to pick some kind of blue color. So let's try 21. So 20 was white, so let's try 21. Okay, like let's put it in every palette, doesn't matter. Okay, let's compile it and let's reload it, and let's see what's gonna happen. Reload. So I was wrong. So basically the first one is background and the second is the sprite. So let's put the comment so I'm not gonna make mistakes again. Sprites, and this is the background. Okay, so let's I should did the Control Z. Okay, so let's make it blue. It's gonna be blue stars. Okay, let's compile it again. We need to compile it every time, and let's reload it. And here you go. That's what I wanted. We have hello, but we need to put world somewhere. So that would be like full combo. So as I said, I want to make the world as a part of the background, because like there is no world inside of the sprite graphics, so it's here in the background tiles. So now let's create another subroutine. So we have palette, and let's create a subroutine that's called put, or I don't know, create world. Create world. And let's put the return RTS. So okay, so we're going to use the same thing we used for the palette. So we're going to basically writing stuff to the PPU. So let's read the address 2002. So we're activating writing to the PPU, and now let's put some kind of address. So it's going to be the higher byte first, I think. So for that, to know where to put this world, like for instance, I can Like for instance, I want to put the world like, I don't know, maybe somewhere here. World. Alright. So we can actually see the address. So let's put it here. 024B. No, I don't know. 24B. Okay, let's try this way. So let's put the higher byte will be for the so the screen has like maybe I will tile map view. So basically the screen has like show the limit. Yeah, so basically the screen has like two name tables. So one is here. So we're using the horizontal mirroring. So those two are mirrored. So we have one name table and second name table. So this one has the address tile map address 2000, and this has 2008. So we're not going to use this, but we're going to use this one. So let's, oh, I can actually, okay, so let's put it 2000, wait, what was that? 24B. All right. So let's put it 24B. So let's put it 22. So that's higher. Now let's store it to 2006. And now let's put 4B as the lower byte, 16 byte address. Okay, 2006, and yeah, now basically I can set the bytes, and those bytes will be the values of this tiles. So this tiles value is 1. So if I load 1 and then store it to 2007, and now I need to call this subroutine, like let's call it after initialization, because we don't need to like change the tiles every frame, because they are not gonna change every frame, so it's not necessary. So let's put it after we loaded the palette, set the variables. Let's call it here create world. All right, let's compile it, and now let's game reload RAM. So boom, the W's appear. But now I want to set the whole world. So I need to. So I don't need to increment anything. I just need to store other values like of this tile. So the O is 2. So just I'm gonna load 2. Right, and I'm gonna store it to the 2007. So the PPU will increment the address itself. So it's gonna be by default it's gonna be the next cell in the grid. So let's save it, compile it. So I'm gonna show that that I'm not lying. Okay, so reload, boom. So we can actually put all the tiles. I mean, this type of, like, if you want to change the background during the NMI, it's gonna cost you a lot, because like this type of writing directly to the PPU is very slow. So try not to do that very often. So okay, so actually I can actually rewrite it later, make it smarter, because like writing like this is kind of dumb. Okay, so WOR load world L 4, store it to the 7, load 5, store it. So this way of coding, like that's it's only children code like that, so don't do that. I will show later how it could be improved, so let's just, for learning purposes. So let's compile it. Alright, and reload the RAM, and boom, we have Hello World. So okay, I will show how can this how we could improve that thing. So we can use the one of the CPU's register, for instance X. So let's load 1. So let's load a value 1 to X register. Okay. So now we can actually delete that, and let's replace store. So we're storing value of X into the 2007. So let's store it. Oh crap. That doesn't matter. It doesn't matter because I'm gonna delete everything. So let's load this and store this here. Okay. So we're going to, of course, we're going to increment X. Now we're going to compare CPX. We're going to compare X with value 6. So if the value is, so we need to branch, so we need to create a label here, loop. So we need to jump to this label if the value is less than 6, and we need to use branch CC, I think. Yeah. So this means that if the value is less than 6, we're gonna jump to the loop. Ah, crap. All right. So we're going to jump to this label if the value is less than 6. So we don't need that thing. Can delete it now. If this is gonna work, like look at this, like it's much better than it was before. So it's much shorter code. So let's compile it. I'm not sure if it's gonna work. I just made a guess that it's gonna work, but who knows? And it's working. So it's, I think it's way better now. Yeah. So you can write like a little kid, like setting like I did here, but you can be a smarter person and write some smarter code with using loops. So yeah, I'm not gonna rewrite this. Like you can try it on your own if you want. So okay, so the last thing I want to do is to make that you could control this, like this hello, and you could move it around, so it would be more like a game. So for that we need to read the gamepad port. Let's create a subroutine that's gonna read the controller. So let's put it, I don't know, here maybe, and call it read controller. Oh, I messed up this one. There it is. Alright. So okay, so we have this here, read controller. So now I need to use another address. That's so it's 4016. That means it's the controller of the player 1. So I need to store something in it. So I need to load a, I think it should be 1. Yeah, it's basically, I think it's, if it's 11, it should be like player 3. So yeah, so it's, or maybe, yeah, it's player 3 from the multi-tab. So basically, if 1, it's, and 4016, it's gonna be the player 1. Now I need to store 0 into this address. That would mean now the controller is in serial mode and it's ready to be read. The data is ready to be read. Now we're going to use a loop. Now we're gonna load a we're gonna load 8 to register X. Okay, we create a label loop. So we're going to read stuff from this address 4016 player 1 controller. Now we're going to shift the data. So basically we got some kind of a byte from this address. Now we're going to shift the bits right. So we're going to use this. So basically, if we got 1 and if we shift it to the right, this 1 bit will be moved to the carry flag, and then we can use instruction roll, and it will shift that bit from carry flag to the, actually we need to create a variable for that. So we're going to specify segment. So we're going to use finally 0 page for that. So I think what's the name? 0 page. Yeah. 0 page. So we're going to create a variable buttons, and it's gonna be a single byte. So that's 1. So buttons, basically 1 byte. So every bit of this byte will be some kind of a button press. So okay, have the variable. So basically we shift that bit that fell into the carry flag into this variable. So it's gonna rotate left. So it's gonna, yeah, so okay, let's buttons, put the buttons here, right? So now we need to decrement. So we previously used this instruction inks. So there's opposite instruction, that's decrement X. So we're going to subtract 1 from this. So it's gonna be, in this iteration would be 7, decrement X, and if X is not 0, branch not equal. Basically, if it's not 0, then we're going to jump to this loop. So yeah, so now this way we can record all the button presses at one moment in this variable buttons. Alright, so now, so in order to test it, we need to put this into NMI, so it would be executed every time, for basically after every frame. So jump subroutine, read controller. Alright, so let's compile it. Alright, and game will run. Nothing's moving yet, but it will. So let's go back to the update hello subroutine, and now we need to change this, change these variables, hello x and hello y. So basically, we need to load buttons. Okay. Now we're going to use a logical operation and to check certain bits from this button variable. So okay, I need to put a binary numbers here for the certain bits in this. So let's 1, 2, 3, 4, 5, 6, 7, 8. All right. So I need to check 4 bits. So let's copy that 4 times. And here, since this AND instruction changes the contents of this register, I need to copy this before AND. So every time I will have the buttons intact. Okay, now I need to. Okay, so now I need to check this bit. Now this. Maybe I should like do like this normally, like this. Now the third bit and the fourth. So every bit is some kind of a button press. Alright. So if the AND finds, I think, if the result of this AND instruction is 1, then means the button was pressed. So, but if it's 0, I need to jump to next check. So if it's 0, I need to go. I'm not sure if it's yeah, I think it's if it's 0, but don't count on my word. So let's check the next button, and next button I think is left. Let's create a label. Go left. Let's make it a local label. So, or maybe not go. Let's name it check left. All right. So check left. Check left. Okay. So if it's right, so basically this checks if the D-pad is pressed right. So if it's D-pad is pressed right, we need to increase. So we're going to use different instructions. Inc, and we can with it we can increase a contents of memory. So we're going to use a variable hello x. So we're going to increase the value of this variable. All right. So check left. So if it's not left, then we need to check. I think it's next will be the next button will be check down. Check down. So let's put a new label. Check down. So it will go here, and if it's actually left, then then we will use different instruction. It's dec. So we will decrement hello x. All right. So now I'm gonna check if it's pressed down. So if it's not pressed down, let's move to check up, and here we put the, come on, check up. Okay, so here I'm going to, so it's down, so we're going to increase the value, so it's going to be inc hello y. And here actually there could be another button, so we need to check. So let's create a label, update sprites, and we shall jump to update sprites if this button is not pressed. So let's save it and let's compile it, and it compiles without problems. Let's try to reload the ROM. Okay, I can actually control it left and right, but it moves by itself for some reason. That's not right, so we need to fix that. Okay, what went wrong? So load buttons, so it moves by itself down. Well, why? Oh, okay, I didn't add the, I need to add here. Why it's moving down? I don't understand. I need to add decrement hello y. Okay, let's try it again. Compile. Where's the game? Hello run. Okay, it's kind of slow because it's incrementing by 1 pixel, so it's pretty slow, but it actually works. So yeah, that was my goal of this video actually, and I successfully completed it. So here you go. So I think I will create a probably, I don't know, probably Git repository or some kind of, I think I will add some kind of a download link for this sample source in the description of this video, so you will be able to download it and try it for yourself. It's not that long, it's like 200 lines, so this piece of code can be vastly shortened because like it's like stupid code. So yeah, that's about it. So that's what I wanted to show you. Well, the video got a bit too long, but I hope it was worth it. Thanks for sticking till the end. Thanks for watching. Yeah, so next time, probably in the next video, I will tell a bit more about my game progress. And if you like this video, so leave a like, write in the comments what I did wrong, and yeah, if you're interested in content like that or in my NES game, then please subscribe to the channel. So thanks again for watching, and see you next time. Bye.